Invitation. I'm really happy to be here and give you a talk on SYK model with global symmetry. This is based on this paper. First, I will introduce the SYK model with global symmetry, starting with the review of the original SYK model and introduce this global symmetry, and then talk about a little bit Largian expansion. Then I will talk about the emergent symmetry, and I will show that how it broken and leads and it gives some effective action. After that, I will talk about the 4-point function, and from the 4-point function, I will discuss spectrum, and also talk about the out of time of the correlator and the Latour exponent. And let's start with some collective field theory of the SYK model. So SYK model is a very simple quantum mechanical model. Here, I think many of you already knew this a lot. And today, I will just talk about the Majorana fermion. It can be also generalized to some complex fermion, but for simplicity, I will talk about the Majorana fermion. So we have n Majorana fermion, and the action is very simply given by this kinetic term and this interaction, quartic interaction term. And this SYK model is featured by this random coupling constant. So this coupling constant is random variable which follow this Gaussian ensemble. For the correct the disorder average, you have to do this quenched average, which means that you have to perform this disorder average of the free energy, not the partition function. So the averaging over the partition function is correspond to annealed averaging. And most of you probably already know that this annealed averaging and the quenched averaging is totally different. But this SYK model case, it's known to be same in Largian. Rigorously, like a Grau already showed that they are same in Largian case. So this is a little bit special case. And quenched average case, for this quenched average, you have to do the replica trick. This is you already know in the this replica trick is well known, for example, in linear entropy, and this is very similar technique.
Which two averages are same, you said?
Quenched averaging and annealed averaging, which is basically when you average it, you can ask whether you have to average the partition function or free energy. Free energy is log of the partition function. So average of partition function is very easy. However, average of the log of the partition function is slightly different. So it's a little bit difficult. To perform that average, you have to do the linear entropy, you know, the replica trick. So as you know, remember linear entropy, you also calculate some kind of log of something, and you introduce a replica space, and do the now and take n goes to, in this case, n goes to 1. N goes to 1 limit. And this case is, yeah, so it's a little bit, in general, it's different, but one can show that they are same in the end. So technically speaking, this is a really typical step, but most recently people just assume that they take a replica symmetric answer and just do the calculate. So you just practically you can just anneal the average in this case.
So you were saying that the equivalence between the quenched average and the annealed average is now rigorously shown by Grau, or which?
Just a particular case. There is a lot of SYK model case, yes. But Carlar's SYK, which is the simpler version of the Gross-Rosenhaus model. For that case, he showed that in Largian they are equivalent. But it's still open question for this Majorana fermion case. But people think it's okay, and some numerical evidence. And let's go. So there is also another quantum mechanical model which is exhibit the similar behavior. Here, TIFR people already people study this tensor model in detail. And this model is discussed a long time back, but it's survived by Witten. And after that, there is many series of paper. And compared to the SYK model, this tensor model is SYK model has a vector index in ON vector, but in tensor model, it should have rank at least rank 3 or rank 5 or rank 7. Odd should have odd rank. But here, tensor model does not have random coupling constant. So this is a really genuine quantum mechanical model. So, but they exhibit some similar behavior. Of course, there is quite different, some different behavior, and there is also pros and cons. Of course, SYK model, cons is the random coupling constant. As we discussed shortly, this random coupling constant from the beginning very hard to discuss. Rigorously speaking, you have to do the quantity averaging, and it's a very complicated calculation, and you have to do the replica trick. And from the beginning, it's very difficult. But if you just take a, let me ignore that issue, just take a annealed averaging, because many people do the annealed averaging, and then this kind of problem vanish. However, in the end, you have to answer the what is play role of this random coupling constant in the holographic dictionary. So this is a little bit, in my opinion, this is a little bit cons in the SYK. But in tensor model, there is no random coupling constant. You don't have to bother with such kind of issue. You just do the usual the ADS-CFT. However, tensor model in this TIF people already point out that the problem is there are too many invariant operators. That is source of the problem. So I will discuss more detail in next section. But so because of that, it's really hard to analyze. But on the other hand, SYK model is basically it's a vector. So in vector, there is only one invariant operator, which is two contraction of two vectors. So there exists the corrective action, which means that you can understand it as just the effective action of this invariant operators. So that in this case, effective action for the bilocal field. On the other hand, as I said, tensor model, such kind of effective action is not known. Of course, there is some kind of attempt, like this my one of collaborator, Robert, also studied some kind of subsector of the such some large invariant operators, and studied such kind of effective action. Also, TIFR people consider the very simple invariant operator and trying to construct such an effective action. So the full sector is not known. Now, let's go back to the SYK model. So SYK model is basically a vector model, OM vector model. And in large N limit, such a OM vector model can be expressed as a bilocal field. So this I is sum over. And this is actually very simple object. This is just analogous to the radial coordinate in the large D dimension. So just when you go to, if you know your system is rotationally invariant symmetry, then you can write down your system in terms of the radial coordinate, and you can simplify a lot of calculation. Likewise, it's if there is or if you consider the ON singlet sector, this is a proper operator to express your path integral. And of course, this is already done in the 3D case, and there is nice relation to the higher spin gravity. But let's keep this one in this talk. And as we discussed, so vector model case, there is only invariant. But as you know, matrix model case, there is infinitely many series of. But still you can control it. So that's why the like a Spenta or the also Gautam did like a matrix model. And you can already control such kind of infinitely many invariant operator. But even if you allow here, this is you can consider some kind of local operator, so the same time. But if you allow the different time, like in this case, bilocal or some other non-local structure, also metric case is infinitely many, too many, like it's kind of word problem. So you cannot control it. Even tensor model case, it's very hard to. There is infinitely many such an invariant operator. So this is some kind of very advantage of such kind of OM vector model. And one of the important aspects of this bilocal field theory is that you can consider this bilocal field as a matrix in bilocal space, which means that this you can, if you consider it as matrix, so this tau 1, tau 2 is a matrix index. So that you just consider the, instead of the usual the discrete matrix, you can consider the continuous matrix. And the matrix product, or we can call it the star product, is naturally defined as follow. This is nothing but generalized of the matrix product. Very simple. And then, as in the radial coordinate case, when you go to the from the Cartesian coordinate to the radial coordinate, there is Jacobian. You can also expect that there will be non-trivial Jacobian here. And if you just forget about the last two terms, this is really same as the Jacobian in radial coordinate. So this is R square, and if you, this is kind of dimension of the Cartesian coordinate. So it's nothing but the Jacobian of the radial coordinate. However, there is one more structure, trace log. This trace log is metric trace log because we consider this psi as a matrix. So this trace log of is the metric trace log of that bilocal matrix. And this additional k is actually come from the, in this talk, this additional constant is not so important because we are only interested in the quadratic action and the result of the four-point function. And you can just derive it. But this k come from the size of the momentum space. So that this is parallel of the counter term when you calculate the one free energy. So that when you construct bilocal corrective action and calculate the free energy, and there is divergence. And if you this term naturally cancels such a divergence.
So this is an exact expression for the log of the Jacobian, or is it like some leading large n expression, or what?
This one is, I would say, exact large n, in large n, but you ask the subleading. But here, whether this kind of discussion is also okay at finite n or not, you can ask that such a question. And for that kind of question, this kind of this procedure is only work in the large n. The reason is that, let me discuss briefly. This is like a, if you consider this one, is now, let's count the degree of freedom. There is n fermion here, and if you go to the momentum space, there is, let's say, there is, in the momentum space, there is k such a field in the momentum. You can discretize in the momentum space. And here, overall, you start from the k times, I have the value right now, k times, roughly speaking, n field. And I will express our path integral in terms of this bilocal field. Right? Then they have k times, roughly in momentum space, k. So I would like to use that they are all bilocals are independent. So that's why it's, if this all the bilocal is not independent, it's hard to calculate, right? So if I want to do all the bilocal are invariant, you should impose such kind of inequality. Because you cannot go to the higher dimension. If you go to the higher degree of freedom, then you need some kind of constraint, which means that all bilocals are not independent. So that the only chance is you go to the lower dimension, lower degree freedom. So that you need this kind of condition, so that n should be much greater than k. K is also essentially infinity. So essentially, this kind of old discussion is only working in large n. But this Jacobian itself is the finite, and it's exact answer.
But it's initially, as you say, the number of degrees of freedom was kn.
Mm-hmm.
Now I'm going to kk.
Yeah.
So I'm like in matrix models,
Mm-hmm.
the transformation from the Mij, the matrix elements, which are n square in number.
Yeah, that's right.
From that, I'm going to, let us say, all the single traces and double traces and so on. So there I know that I'm discarding the angular variables. I'm actually going to eigenvalues.
Yes, exactly.
Okay.
Yes.
So therefore, I have this van der Waals determinant and whatnot coming from the integration over the angles.
Mm-hmm.
And I also say that whatever operators I have, they should be only functions of eigenvalues.
Yes.
Okay, so here you say that, well, nothing colored should enter my correlation functions, and so there also, however, this issue of the Jacobian,
Mm-hmm.
even from going from Mij to the eigenvalues,
Mm-hmm.
is a complicated issue.
Yeah.
Because it's a rectangular matrix.
Mm-hmm.
The Mij is one kind of variable, and lambdas are some other kind of.
Yes, that's right.
Sorry, I should say it differently. The density of lambda versus the single trace and double trace.
Mm-hmm.
They're different kind of variables, and I don't think there is any exact calculation of the Jacobian of this thing at all. So I'll be interested in knowing how this is arrived at, if this is exact.
There is you can also deal with n equal, for example, 2 and k equal 2 case, or n equal 3, k equal 3 case. You can also calculate such kind of mapping exactly.
And it works out to be this way? It works out to be that?
Yeah, it turned out to be, it depends on the, yeah, so.
So you put tau on a lattice of 2, you put tau on a lattice of 2 points?
Yeah, you can just say that, for example, you can consider psi I like 1 and 2. And you can also work out a little bit.
Okay,
but I will show, in detail. So.
If there is an exact answer like that, that's interesting. Even from the point of view of the old matrix model, that's an interesting issue.
I see. Probably, but at some point, I will discuss more detail, some other way to think of that. But let me talk about that later. So now I will extend this bilocal field. So if you add some additional structure to the fermion, you can easily extend to that is also this bilocal field also incorporates such kind of a structure, and it just leads to the extension of the bilocal space. So then now previously it's just bilocal in time space. Now it's bilocal in time and the additional structure. So that accordingly the matrix product is also naturally generalized in this way. And for example, one can consider such an extra structure is replica space. So we also discussed replica trick, and you have to introduce the replica space. Then you can also work with this alpha now can be the replica index, and you can consider some bilocal field theory of the replica space. And you can also work in that, and then you can take a replica answer. You will end up with rigorously end up with the original SYK model. Another example is Sommerfeld dynamics. And the thermal field dynamics, you have original system and some double system. Or you can consider the right shifting or left shifting in the ADS shifting. And you can label one of them is 1, the other is alpha 2. And you can also work with such kind of bilocal field of the thermal field dynamics. So that tau 1 component is living on here, tau 1 2 is the crossed, and the tau 2 2 is psi 2 2 is live here. So this case is already discussed is a 3D case, and it gives some results, but I will not discuss this part in detail. And this alpha need not to be a discrete index. It can be even Grassmannian variable. So if you think if you add some Grassmannian variable, this is now bilocal superfield. So this appears in the supersymmetric SYK model. In the supersymmetric SYK model, you start with the superfield formulation. And it's natural to construct a bilocal superfield. And then what you have to do is bilocal in tau 1 and theta 1 and tau 2 theta 2. And you can work out in the similar way. And today I will add flavor index. And this also gives this kind of give the extended bilocal space.
So the couplings are not going to have this index, right?
J, in general, you don't have to. Yeah, that's right. But it's your choice. If you add it on, but it's non-trivial, you can have to. But it's your freedom to.
So you would have to make a singlet in the flavor space.
Yeah, for example, yeah, in this case. Yeah, that's right. So it's a very easy generalization. If you add some flavor index to the coupling constant, some other generalization. So
I have a more basic question. I mean, usually when we change the variables, we don't really talk about non-local fields, right? In 3D also we could have done that, but we don't do that. We just take singlets, local singlets, right?
Yes, that's a good point. Yeah,
so why is it that we want to consider
non-local object? Okay. First of all, I try to avoid that. Actually, I have that slide, but I erased it. In the higher dimension, also there is some such kind of non-local construction. So that is involved the higher spin theory. And even there is two types of the construction. One is Hamiltonian formulation, the other is Lagrangian formulation. So which means that you have, roughly speaking, you have a OM vector field, and you have a time one, and you can consider space. Or you can consider the same thing, but so difference is that they are non-local in the spatial space, both are. But the difference is whether time is local or not. So SYK model case is non-local in time. This case you can also consider the time is the same. So this is we call it Hamiltonian formulation, and this is Lagrange formulation of the collective field theory. So this is already studied by the Antal and the Sumitas, and they calculate some free energy and so on. And for this one, you can basically consider this time is fixed, and this corresponds to the, so for example, 3D case. This is 1 dimension time, and the 2 dimension space, and 2 dimension space, this y, x. And this corresponds to the higher spin ADS4 time, and some coordinate, let's say, roughly speaking, x mu, x, and this is 4. And there is additional variable spin s. So there is map between there is 4 plus 1 degree freedom. Here also 1 plus 2 plus 2. So that you can find some kind of map between them. Also time is just fixed, and the 4 bit. So this you can also do that in higher spin context. Yeah. So it's not special in the 2D. Or, yeah. And just one thing is just a very simple dimensional reduction of this case is just correspond to the SYK model. So for example, you remember that this in SYK model you have tau 1 and tau 2, and this tau 1 later you will see that tau 1 plus tau 2 over 2 is not so important. Tau 1 minus tau 2. This player over time, this player over the some coordinate in the its behavior like some z coordinate in the ADS2 Poincare coordinate. So this is somehow very similar to the higher dimension. And let's go. So here, this is very similar to the original SYK model, but I add this flavor index alpha. So alpha goes to the 1 to m, and m should be much smaller than n. Otherwise, you cannot use the large and diagrammatics of the original SYK model. So if you very close to each other, then you have to calculate again without. And then one aspect of this action is manifested in SOM invariant, so that I contact this alpha, and here also alpha 1, alpha 1, alpha 2, alpha 2. So this action is slightly different from the previous three model. So Sachdev and their collaborator study U1 case. Definitely there is no U1 charge. There is no flavor index, but of course they are very similar. And the Gross-Rosenhaus also add the flavor index, but the slight difference is that they don't have contraction. But essentially, the results are very same, up to quadratic level. If you go to the cubic and higher, then it will give some different answer.
So what do you mean they don't have contraction? You mean that now J's include the alpha?
No, in their case,
in the Gross-Rosenhaus case, you were saying
this is alpha 1, alpha 2, alpha 3, alpha 4. That is a chart like a colored SYK model.
They're just hanging around this alpha 1, alpha 2, alpha 3, alpha 4. I mean, is there? No, wait. What do you mean? They're just hanging around. There's no.
Yeah, so actually that is slightly related to our next follow-up paper. Actually, they consider the very general flavor structure. So, of course they don't have such just without contraction, just that alpha is add. But later there is a way to, because basically this using the SON case, you have two types of the invariant tensor. That is here I using one of them delta. There they use epsilon. So I mean you also have to some generalize their formulation.
They have some epsilon contract.
Actually,
What do you mean?
they didn't include it. Just from the beginning, they just more complicated situation, very complicated. Like consider the J, if you read their paper, chi alpha 1, chi alpha 2, and this is related to some one flavor, the other one flavor. And the simplified version is that color is more like a alpha 1, chi alpha 2, and so on. Is very similar, but it's slightly different. But in the end, it's the same. Yeah.
And the Sachdev's paper, the 1612, that of course does U1. So
U1, both are U1. Yeah.
So
Yeah.
you will continue with Majorana.
Majorana. But this case is also very similar, easy to go to the SUN, because nothing but you change it here and add here, and J is slightly Jij, KL. So you can also generalize. And that is also discussed in the appendix in our paper. And so here's, you can also define Bilocal fields as follow. So here, this can be think as you can consider this bilocal field as a matrix in the expanded bilocal space. So as we discussed, and the corresponding star product is very simply generalized. But here I separate the alpha index from this tau index. So sometimes it's very useful to separate and consider this bilocal field as m by m matrix. So that this is a bilocal field is m by m matrix of the bilocal field. So that this is in next slide you will see that this is very useful. So now let us discuss how to give the construct a collective action. So you have kinetic term. First, let's consider kinetic term. Kinetic term can be easily write down as follow by using bilocal derivative in this way. This is just nothing but rewriting here. And the next one is Jacobian. Jacobian arises when you go to from this vector fermion to the bilocal field. And I already discussed this one very naturally. And you have this one. And here, I'm using capital trace. So this capital trace run over the extended bilocal space. So, but on the other hand, small trace is run over the flavor index. So I will soon explain this part. And this is nothing but come from Jacobian, and the final term is from the disorder averaging. So you have this interaction, and after disorder averaging over the Gaussian ensemble, you will get this term potential. So now this small trace is running over this flavor index, and in general, this term is nothing but linear combination of Schur polynomial of this matrix. Now this is m by m matrix. Let's forget about the time space because time is not, in the end, you just integrate it over. And this you can consider it as m by m matrix. And here, this is not Schur polynomial because this is sum of the Schur polynomial. So depending on how you define this interaction, you will get the various type of the Schur polynomial. But this is not so important because in the end, it gives the same result up to quadratic level. From the cubic level, it gives the maybe different results. But up to quadratic level, it's the same result. So that I just consider the simplest case, which is this case. So next thing is you can consider large N expansion. This is nothing but you varying the action with respect to the bilocal field. And then you will just multiply the matrix side, and we will get this equation. This is nothing but Schwinger-Dyson equation for the two-point function. And some of you already realize that this can be derived from the large N diagrammatics of the SYK model. But if you're using this variation, this you can very simply obtain without any diagrammatics. That is some advantage of this problem, this method. And then we will solve this large and saddle point equation. We first consider the strong coupling limit. So at the strong coupling limit, you can drop this first kinetic term. You can easily see that by absorbing this J into the psi, this will be suppressed by 1 over J, scalar to J, and this is, you can neglect them.
What happened to log psi?
Log psi, here, you first variation with psi. Then the psi inverse and the multiply psi, then it becomes identity. So actually, they come from the log psi, and they come from the interaction. And then we will take a SOM invariance ansatz. So which means that bilocal field is proportional to m by m identity matrix. If you take this ansatz, then you just plug into this equation. Then you end up with the original the single disonification of the original SYK model. And you will realize that this is nothing but the matrix equation. It's not so useful for now, but this is identity, and this is, you can consider matrix, and this part is inverse of this matrix. So this is a very simple equation. And there is, people already found the large and classical solution, and you using just use the large and solution. And the one thing is that we take this SOM invariant answer, so that in flavor index, it's symmetric. So that's why this time space should be anti-symmetric. So that's why we have this kind of anti-symmetric solution. And let's go to the emergent symmetry and the effective action. So as we discussed in the strong coupling image, you can drop the kinetic term.
So are there other saddle point solutions also in which it's more complicated than what you have? It's just identity times the old saddle point. Are there other solutions also?
You have to break the SOM symmetry,
Yes.
SOM global symmetry. Yeah, of course, you can do that.
But is there some energetic consideration or something which will say that this is the lowest?
This one? For now, I just take a SOM answer because we start with the SOM invariant, global invariant theory. But you can freely, and even this is the SOM case, SUM case, you can also do the, so for example, even this flavor index is symmetric, this time space need not to be anti-symmetric because you have now complex fermion. So there are more fruitful discussion for that. So
is this the dominant saddle point?
this one, I didn't think of that. Yeah, but yeah, I expect that would be.
Okay.
So in the
Corrections, if you were interested in corrections, they would not just be 1 over n, but you would have to take into account all these saddle points.
yeah, if rigorously, but if you keep the global SOM, so now the whole story will be changed, because if you don't keep the SOM global symmetry, the whole discussion will be changed, and you also talk about So that is a good question. Yeah, one have to in the end consider some other saddle. So now you can drop at the strong coupling image, you can, as we discussed, we drop the first term in the single disonification. For the same reason, you can ignore this first kinetic term. Then you will see that as usual in the original SYK model, there is emergent reparameterized symmetry. Under this transformation, this action is invariant, because this is trivial because this vector is cancelled with the Jacobian from this vector. And the log is nothing but this will be, because this is a matrix log, and this will be separated. So that up to some constant which is nothing to do with this field, and this action is invariant. In addition to this emergent reparameterization, this global SOM symmetry is enhanced to the local SOM symmetry, which means that you have this bilocal field. This is n by n matrix, and this is transformed as the G times psi to the times G inverse. This is very similar to the sigma model or Westminster-Witten model transformation. And in the Westminster model, this is Z bar. But here it's tau 1, tau 2. And so that's why I say local, because it depends on time. And if you consider both of them together, they are not direct product. The hypermorphism and the local SOM is not direct product, but it's a semi-direct product. Because the reason is that now the local transformation also depends on time. So that if you keep transforming, and it's not they are related to each other. And if we work out this algebra, and this is pointed out by Presby, and it gives Virasora and SON Katsumudi. Of course, without central extension, because for the central extension, you have to work very hard with like a cojoint orbit or rigorous quantum calculation. But here, this is almost classical calculation. You will not see such kind of correction.
Just one sec. So go back to the previous slide. Yeah. So the saddle point solution breaks almost all of the reparameterization besides some SL2. But here, the saddle point solution.
I will discuss. Yeah. So
the structure of Goldstones would be very different. I mean.
Yeah, so because for now I didn't discuss the classical solution. This is nothing but symmetry of the action. Yeah. So next slide is that. Yeah, symmetry breaking. so we have classical solution. We already see that. So this is usual SYK model classical solution times the SOM invariance answer. And first of all, this kind of emergent symmetry is spontaneously broken by this classical solution. First of all, as you know, the reparameterization symmetry is also broken. And this global symmetry is also, local symmetry, SOM local symmetry is also broken because time is different. So if you, you have G1 tau 1 and the identity matrix G inverse tau 2. But they are different time. So it's not the symmetry of the global symmetry. So it's, but if that is global, it's invariant. So that it's a very similar story, like I will point out later, next slide. But this classical solution is invariant under the SL2 and the global SOM. So that's why we choose this one. And also, this is so far talk about the strictly strong coupling limit. But now, if you go to the large but finite coupling constant, then you cannot ignore this kinetic term. Then this kinetic term, you will realize that this explicitly breaks the two symmetry because both of them depend on the time. So that you will have some kind of pseudo-Goldstone boson and the effect of their effective action. So how to calculate it? You first have a classical solution and transform it by using this kind of F and G. And plug that into the kinetic term, which break the symmetry explicitly. Then some calculation, you will obtain this kind of effective action. So first one is well-known Schwarzian, and you know that this is SL2 invariant. That is also regional because the classical solution is also SL2 invariant. I mean, the vanishing under the SL2. And the second one is the action of a particle on the group manifold, because this is trace Jj. J is nothing but this current. And this comes from the local SOM symmetry, and this one is vanishing under the global SOM, of course. And actually, this also you can obtain by cojoint orbit. And here, Spenta and Gautam already obtained this Schwarzian from the cojoint orbit. And actually, this term is also obtained from the cojoint orbit. And in fact, that fact is already pointed out by Witten and Stanford without any model. Because they know that there is such kind of cojoint orbit, and you can construct such kind of effective action that is one loop exact as usual in SYK, as in the Schwarzian case. Also,
but in the in the thing that we're doing right now is in the U1 case, there is a coupling between this G degrees of freedom and the F degrees of freedom.
Here, no,
so
because
you don't have any.
Yeah.
So is it because there is no U1? Suppose there was a U1. And you have some.
Yeah, then U1 case.
Potential for the U1.
Yeah, U1 case.
If there's a coupling between the F degrees of freedom and the G degree.
Yeah.
You don't have that.
We don't, because the reason is that they are using the SOM invariant answer. All of them is related to the SOM invariant answer. here. So, for example, let's assume that if you have this kind of, let's just by put by hand, that term linear, like a j plus some kind of a derivative or some epsilon I trace square. And if you expand it, this is j square. And the next term is j times roughly speaking del epsilon trace. But this j is the current j. And as you know, this is traceless matrix. So that this will really just become 0, right? J is trace. So the difference is that all involved with the diagonal part should be diagonal part, such kind of interaction. So that is, so you have to go to the U1 or UM. SUM also you don't, so. And the super Schwarzian case, this you can also do this same calculation. You can also obtain the super Schwarzian in the supersymmetry SYK. And now let's go to the spectrum. So bilocal field is now defined from this fermion, and the fermion contains the fundamental representation. And this is a very simple group theoretical fact that two fundamental representation will be decomposed into the singlet and the anti-symmetric and symmetric. And for example, SUM case is a singlet and adjoint, but yeah. And then you can also consider each sector, singlet sector here, singlet sector, and the anti-symmetric sector, and the symmetric traceless sector. And if you see here, this is a well-known fact in large N that there will be a disconnected piece in the when you calculate this 2-point function of the bilocal field. So I forgot to mention that this is a 4-point function of the fermion, which corresponds to the 2-point function of a bilocal field. And then there will be some leading end disconnected piece. But here only singlet sector has a leading disconnected piece. The reason is that we took a SOM invariant answer. So that's why we have such kind of leading disconnected piece in the only singlet sector. Others does not have. And now, in order to calculate the 4-point function, you have to calculate the quadratic action. For such quadratic action, we will consider the fluctuation around the classical solution. So that you have bilocal field, you can expand around this classical solution, and these are fluctuation. Also, fluctuation consider also decomposed into the singlet and anti-symmetric and symmetric. And as you see here, singlet and symmetric is symmetric in the level index, which means that they are anti-symmetric in the time space. On the other hand, anti-symmetric representation is anti-symmetric in the level index, which corresponds to the symmetric in time space. So this kind of property is have changed result quite a lot. So which means that this singlet and symmetric has a little bit similar behavior, and the anti-symmetric shows some different behavior. So, and if you just consider this large N expansion, and you can obtain the quadratic action of this fluctuation, and you will get this term. And they are all decoupled. And if you diagonalize this quadratic action, you can easily calculate the 4-point function of fermion. So that is basic idea, but I will not show explicit calculation because this is really a complete case calculation. But I want to point out one thing, that this coefficient, difference coefficient. If you see here, the singlet sector, quadratic action of the singlet sector and the symmetric traceless sector, the only difference is this coefficient. Because these are so when you calculate when you diagonalize this quadratic action, some of you already know that there is zero mode in this singlet sector. This singlet sector is nothing but the same as the original SYK model. So you know that there is some kind of a zero mode and which make a 4-point function divergent. However, if you do the similar calculation, because the coefficient is slightly different, so you can expect that the zero mode here will not the zero mode of here. So that you will, in the end, you will realize that there is no zero mode for this symmetric trace list.
So you mean that there is a finite answer in the limit of beta j going to infinity in the in that?
Yeah, there is no divergence. Yeah. So that all consistent. I will show some relate to the effective action and so on.
So wait, you're saying that if you started off with an SOM invariant classical solution and went broke conformal invariance, the zero modes that you generate are all in the singlet set.
Singular, and I didn't talk about this one, anti-symmetry. Yeah, yeah, these two, and quite related, and yeah.
Singlet and symmetry.
Yeah, anti-symmetric. Yeah, these two. So the reason is that I didn't. The reason you can compare these two is that because of these two symmetric property, you can use the same basis for the singlet and the symmetric traces. But for this one, you have to use different basis to diagonalize this action. So that's why you can compare these two calculations so that you can easily convince that. And then I will do, so first you calculate 4-point function, and I will skip all details just so you can take a OPE limit, which is just take this cross ratio going to zero limit. And then you can expand your 4-point function in terms of the conformal block, and you can read off this conformal dimension. And this conformal dimension is determined by these equations. So each one you can do the same thing. And here, let's consider this one. And here, as you see, this h equal 2 is the solution of this equation. So that it is related to zero mode of this 4-point function. And the symmetric case, if you plug in the h equal 2, because of this, so this coefficient, the previous slide, you see that this coefficient difference. Q equal 4 case, for example, this is 3, this is 1. And the Q equal 4 case, this influence this coefficient. This 3 and there is no coefficient 1. So because of the coefficient difference, if you plug in the h equal 2 mode, this is h equal 2 mode is not the zero mode in this case. This not solution, and it's all related. So it's I have to explain in detail, but roughly speaking, h equal 2 mode is not in the spectrum. Right?
But now the group theory is also different. So maybe h equal to 2 is not the right thing to look for. Maybe there's some other value of h for which, right? Because now it's a sort of semi-direct product of the SL2 and.
So roughly speaking, so the divergence come from the it's a 4-point function. If you because you all know the so 1 minus k here.
Yes.
Because and there is some by kind of basis. Right?
Yeah. So earlier in the uncharged, without the global symmetry, you had a spectral decomposition of k.
Yeah.
In terms of the SL2R properties.
Mm-hmm.
Right. Now. And yeah, right. It was only SL2R properties, so it was all given by only the values of h.
Yeah. Okay.
And h equal to 2 turned out to be the zero mode for which there was a
Yes.
answer.
Yeah.
Now it's what?
Same basis. So I just skipped all the details, so that's why it's a bit confusing. But here, when you expand the 4-point function, this one and this one use the same basis.
No, but I don't see why h equal to 2 should again be the zero mode.
Not zero mode. Not zero mode.
Not zero mode. But
Yeah.
I'm saying that this could be solved by some other value of h.
Yeah. And next slide. I will.
Then that would be the zero mode,
No,
which they
that h value does not here. Here when you expand with the discrete series and continuum series of the, you remember there is. So the problem is that this discrete series is like a 2, 4, 6, and so on.
Yes.
And this one make a diverging this kernel here. But if you have 1 over q here, you don't have a divergence here. So this kind of result is when you sum up the whole some spectrum and so. So there is for the basis, yeah. Yeah, so because the reason is I skipped all details. So
I see. So you're saying that it is still given by the SL2 group theory,
yeah,
but a factor of 1 over q has come in.
yeah. So that's why you don't see the. Also tensor model, you can also see the similar behavior. Yeah. And now.
H equal to 2 was he's saying that h equal to 2 was the only point which was common to the original discrete series and after the contour deformation. So that h equal to 2 does remain something special even here. That's
That isn't a simple argument to see why those zero modes don't occur in symmetric fluctuation. You have to do all these things.
Yeah. I will discuss more detail later. But the other here is if you see here, singular and the symmetric traces has a similar function, but the anti-symmetric has different function because you have to using the another basis. Here h equal 2, 4, 6, but here you have to use 1, 3, 5, and some other basis. So that's why you have different function, and you will see that h equal 1 is solution of that, and also h equal 1 is zero mode, which make a divergence. And here, this answer is actually you separate the zero mode and the non-zero mode, and only consider the non-zero mode, because you cannot calculate the zero mode when you consider when you using the conformal symmetry. And here, let's talk about the spectrum. This, for now, this is also known for general Q case. Q is here. We start from the quartic interaction, but it can be generalized to the any n-point interaction. But this can be also generalized. But for simplicity, I use this Q equal quartic interaction case. So singular fluctuation, the spectrum is determined by this equation, and the symmetric trace is determined by this equation. And anti-symmetric by this one. And the only difference is this 2 is the slope of this linear line. So that the red line is related to the singular fluctuation. So that you have 3 over 2 has the first solution. So the relation between h and nu is h equal nu plus 1/2. So that this corresponds to h equal 2, and you have this kind of the solution. And for the large conformal dimension, you will easily see that the difference of the two conformal dimensions would be 2. On the other hand, the anti-symmetric fluctuation, the first solution is 1/2, which corresponds to h equal 1, which is also zero mode. And you will also have this kind of discrete conformal dimension. And the symmetric traceless case is here. Some first one is 1.3434, 2434, and there is also series of the spectrum. And yeah. So this here is the no zero mode because there is no. I will discuss more detail because there is no contribution from the effective action. And let's talk about the out of time of the correlator and the chaos. So there is many ways to talk about Lyapunov exponent or calculate the out of time of the correlator. One way is retarded kernel method, which you can use a real time calculation. But for now, in this talk, most intuitive way and the simple way is to calculate the contribution from the effective action. This is a very quick way and very intuitive. So let's talk about. Let's start from this effective action. So effective action, as we discussed, there is Schwarzian and this trace of the current square. And the first, what you have to do is consider the infinitesimal transformation. So infinitesimal reparameterization and the infinitesimal local SOM. And then you can obtain the quadratic action of this infinitesimal transformation. After that, you can resolve the two-point function of this infinitesimal transformation. And then what you have to do is now how we will consider how to contribute to this four-point function. And the four-point function or two-point function of bilocal fields contain two contributions. One is zero mode contribution, the other is non-zero mode contribution. So for this kind of chaos, it's mostly come from the zero mode contribution. The other one, non-zero mode contribution, give you some correction to that zero mode contribution. So for now, I will just consider the zero mode contribution only. So which means the leading Lyapunov exponent. To contribution to this infinitesimal transformation, you can write down here and consider the infinitesimal fluctuation of this disconnected piece. Here, if you consider this one, and this is without this expectation value, this will be the quadratic part of this infinitesimal transformation, and you just consider the expectation value of this infinitesimal transformation. We know all of them. This one comes from this effective action, and this one comes from this is related to you can easily calculate this part from the classical solution. This corresponds to the actually eigenfunction of the effective action. And then after that, also as we discussed, you can also consider separate the singular sector, anti-symmetric, and symmetric traceless sector of the previous these two contributions. So this is now m by m matrix, but now we have to consider decomposing into each representation. First of all, let's consider the singular sector, which relates to the singular fluctuation. So if you just take a trace, and this captures the singular contribution to the singular fluctuation. However, this reparameterization, if you perform the infinitesimal transformation of the reparameterization, this transformation will not touch the m by flavor structure. It's just multiplication of the function. So which means that this is still the identity matrix. If you transform this delta epsilon, that's still the identity matrix. Which means that if you take a trace, this is non-zero. But if you take a trace with some other generator, they will be just zero because this generator will be traceless. So that's why there will be no contribution from the Schwarzian to the anti-symmetric fluctuation and the symmetric fluctuation. In addition, let's consider the infinitesimal transformation of this classical solution with respect to the local SOM. If you transform this identity matrix with respect to this one, and this will be anti-symmetric and traceless matrix. This is you can just expect that it is related to the adjoint representation, and it's traceless and anti-symmetric. Which means that if you take a trace of them, this will be just vanish. So that's why there is no contribution from the other effective action to the singular sector. In addition, because this is traceless and anti-symmetric, this overlap will be also zero. So that there is also no contribution to the single symmetric fluctuation from the effective action or whole effective action, because Schwarzian does not give contribution, and the local SOM effective action does not give the contribution. So that's why the symmetric fluctuation does not get any contribution from the effective action. So that's why no zero mode, and everything is consistent. So the only non-zero is these two. And I also skipped the whole technical detail, but the basic idea is that so far we just consider the Euclidean formulation, which means that I calculate the 4-point function on the circle. And then you have to perform the proper analytic continuation to the real time. And then this will be related to the, then you can obtain the out of time model correlator. And so by using this analytic continuation, you will get this answer. From the previous slide, this one and this one, you will get this one and this one. There is no contribution to the symmetric part. So singular sector, as usual in SYK, grows exponentially with the maximal Lyapunov exponent. On the other hand, the anti-symmetric grow linearly. And that is a little bit consistent with the fact that the Lyapunov exponent of the spin S contribution is raised to S minus 1 to pi over beta. So this corresponds to the spin 1 case. So that it's not surprising that you have a zero Lyapunov exponent, but it's linear. But here it's not polynomial, but everything is exponentially decreased.
Sorry, just one second. If you go back to the previous slide, please.
Mm-hmm.
So here, I see.
So here Schwarzian give the
reparameterization
exponential.
modes did not contribute for the antisymmetric because
Yeah.
of the group theory.
Yeah. And this contribution always, so this contribution is always give the linear, and the only contribution this row contribute to the anti-symmetric, so that's why anti-symmetric grow linearly.
And the it becomes this t linear in t because the propagator was 1 over n squared.
Propagator, I mean
For the row. For the row fellows, the propagator was just 1 over del squared.
1 over del square, which
As
is
against for the epsilons,
uh-huh.
there the propagator was 1 over n to the power 4 minus n square over beta square.
You talking about the n scaling or the which?
No, the mode n. I'm saying that it's a fourth order propagator action for the epsilons.
Yes. Yeah.
And it's just a ordinary second order action for the rows.
Yes. It's mainly for this one. It just to give the answer.
It's
So
just a Fourier transform of 1 over p square, 1 over omega square. That's what I'm saying.
omega square. Yeah, probably. Yeah, in particular, this is yes. This I will talk about the non-zero mode contribution. Yes, that is somewhat related. But here, yeah, let me think of it. Yeah, probably. Yeah, I agree that it's more like 1 over omega, but I'm not quite get. But anyway, let me discuss that one.
All right.
And here, so this is for the zero mode. I didn't discuss the non-zero mode contribution, but I just write down the result. So when there is a lot of non-zero mode contribution, and if you sum up all of them, you will get this kind of correction. So this looks like seems to be violate the chaos bound. Actually, but it's not. It will give the correction of the to the Lyapunov exponent. In addition, you can also sum up all the non-zero mode of the anti-symmetric part, and this is also you can show that it's linear. These two calculation is related to the fact that they have a double pole structure. I didn't discuss it in detail. So double pole structure comes from the fact that there is somewhat related that there is some zero mode. So that diverges and they become double pole and I give the T here.
Can you repeat how do you understand this extra contribution? You said it doesn't really violate the bound.
He's saying that this is from the h not equal to t thing.
Yeah.
So first of all, in the beta j going to large limit, the second term you can forget about. But because of that thing being so if you take out the beta j, then and the exponential, then it's like 1 plus t over beta j, beta square j or whatever that is.
Yeah.
So it's 1 plus some small object, take that to exponential. Exponential of t.
Yeah. Right.
So then that renormalizes the Lyapunov exponent itself. That's what you say.
Yeah. So yeah, Gautam explained well. So this is basically this kind of t correction can be exponentiated and give the Lyapunov correction. Yeah. So and this is also you can consider some correction to this 1 over beta j correction to this one. And but symmetric channel, if you also calculate the
There would be one time when the contribution from the second part would overtake the first part because you have a linear.
this one or this one?
The first.
First one.
There's a linear t which keeps growing. So would it be possible for the second term to take over the first term at some point?
No, you have to then it's because for now you consider the large beta j limit, so there you don't have to worry about that. So it's the time limit. So you consider the certain time limit between the some here large and so there is you.
Yeah,
So on
there's a claim that there's a linear t term and there's t square.
Yeah,
Whatever
yeah.
it is. Then the actual there is a resummation possible, so that the actual expression is the exponential.
Yeah, that's right.
So if you just have these, of course, then there could be some straddling time or whatever it is, so that the second term is bigger than the first term. But the claim is just like we found this resummation in our kind of series. Okay, there is a resummation like that with everybody around. So there's a renormalized Lyapunov exponent given in Magazin's Stanford's paper, okay, where they give the 2 pi over beta minus whatever it is, and the claim is that's the expression. Then it's actually a Lyapunov growth. Okay. What you see from the linear expansion is just not the right thing. It's a red herring.
So that is the full thing was computed from the path.
Full thing? No. In Magazine and Stanford's field theory paper itself, the expressions are given for the modified Lyapunov exponent.
Yeah. And also, like for example, another question is like if you go to the higher spin theory, there is also a lot of violation. There seem to be violation, but you have to properly sum over all of them. Then give the Lyapunov. So it's more like as I discussed here, Lyapunov spin s is greater than 2. They seem to be all violate, but you have to properly sum over all of them. Then you will realize that their Lyapunov exponent is zero.
But then there are also, if you violate them, in those theories there are also some problems with immutability.
I mean, when you say violate, so naively it looks like violate because you don't sum up properly, as you said here, T also, because it seems to violate, but if you don't sum up properly, then it looks like violate.
Yeah.
In here also, if you don't sum up properly, then it looks like violate, but you have to do the sum properly, and you will give the zero Lyapunov exponent. So for this kind of
Of this tiny exponential, when the Lyapunov exponent in this case is twice pi over beta minus some object, right?
Which one?
In the exponent that you written on the board.
Here?
No, the expression before exponential of twice pi over beta minus epsilon over beta.
Mm-hmm.
So in this case, you would say that the chaos bound is saturated only in the larger limit because that is where the second term is suppressed. Otherwise, this is not saturating the bound, right? It's less than twice.
Yes.
Yeah, less than, yeah.
It's not at the conformal point, so it's not given by gravity. In the sense that it may not, it's going to some, okay. It's not clear how to interpret. But in the field theory, there is no problem in having something which is less than 2 pi over.
Right. I mean,
It's only an
gravity.
hour.
I think it's fine as well as you have to have a black hole or something.
So it's consistent with Martin, the causality thing paper because that's supposed to be an upper bound. As long as it's minus, it's okay. But what he's saying now is that for s greater than 2,
Yeah.
okay, is violating the upper bound constraint. But you know, this is Justin and Survi and their paper shows that in those situations where you violate the upper bound, okay, you also violate something else.
Mhm. Yeah. Yeah.
All right.
So there is so here symmetric no double fold and no even non-zero mode there is no no any growth. It's all exponential decay. So now let's talk about the exponential growth and the linear growth. So we have exponential growth, and if you demand that if you calculate the SOM invariant some observable, which means that you have to sum over the flavor index, then you will have such kind of dimension of anti-symmetric, which is roughly speaking m square. So this is a little bit similar to this tensor model story in the TIFR. So it looks like you have to compare this m square, this one. So even like for now we talk about the finite m, but the m is not necessarily to be small. But you can consider large m, but much smaller than n. Then maybe it's make a problem. But so far, as we see, you don't have to mix between them. So like you can separate the singular sector and the adjoint sector, and you can calculate separately. So they don't have to compete each other. And
wait, are you saying that there is another expansion possible in which m is much bigger than n?
No, this case n is much. In just this case.
So that's all that is available.
Available.
You can't reverse the other.
I cannot. Yeah. Only in this case, still you may say that why if you calculate something and you might have both of them. The question is as in tensor model in paper in the TIFR and they consider the mixed competition between them.
Yes.
So this is like a exponential and this now m square. So
that always wins.
Sometimes it wins this m square. I mean m is large.
It always wins. I mean unless the time is.
Some very small interval, and there is some time that this can be win. Right? So that's the point of here instead of here it's roughly speaking m square t and the exponential 2 pi over beta t, and so in this Shiraz paper this is n square, but instead of n square but m square. But let's say m is much large. It's a large quantity. Then you also have to worry about this kind of competition. But what my point is that does not happen I mean that can be happen, but you don't have to calculate such observable.
No, but the point that Shiraz's paper makes is that for t much bigger than log m.
Yeah.
Then the first term starts dominating.
Yeah, but before then, it should be much greater than, for example, log m, roughly speaking, and much greater than beta. In this, because it should be after the dissipation time and some win. So there is maybe some problem because linear term. So, but so that is just happen. So I'm not sure it's a problem or not. But if someone says that this is a problem, right? Then because you cannot see the linear growth in the if some linear growth cannot dominate in the gravity picture. I'm not sure, so someone claimed that.
No, meaning that there is no Lyapunov.
No Lyapunov exponent.
So in that range of time, Lyapunov exponent is 0.
0. Is it just the answer? Okay. So I'm also happy with that.
It was not clear what whether there is a gravity tool for that.
Yeah. Okay. But my point is that my interpretation in this case is that this anti-symmetric part is not the generic operator, but special operator. Because if you see the anti-symmetric bilocal field, and if you expand in time, Taylor series expansion, it contains some it's related to the SOM generator. And that is very special operator. So that when you talk about the Lyapunov exponent or chaos, you have to consider the generic operator. So that it shows some universal property of the system. But for example, if you're choosing the Hamiltonian, you don't expect such kind of behavior, even though that is a chaotic system. You don't see the Lyapunov exponent. So because Hamiltonian is a very special operator. Likewise, this may be later special operator. So that's why it just grows linearly, and it does not capture some chaos in the system. So
you're just taking 4 fermion, a 4-point function of 4 fermions.
4 fermion, but yeah.
With arbitrary assignment of color and flavor.
It's not so arbitrary because here bilocal field, so roughly psi alpha 1 and 2. And this is, if you anti-symmetrize it, it's actually you realize that this is a generator of that. Yeah, very special. It might be very, so that's why it may be. So this is just.
But I see.
So, and also this one, it's not exactly the same, but because now this bilocal, but you Taylor expansion and then it's kind of contained. So that's why maybe it's, so still maybe system is maximally chaotic, but because we calculated this one, that is special operator, and that's why and even that happened in the also tensor model. Tensor model also has such kind of linear growth, always very special operator, like a lateral generator. So that, all this kind of exponential growth relate to the diagonal part of that one. So if you a little bit separate nicely calculate the 4-point function, you completely separate the exponential growth and the linear growth in tensor model, rank D. And then you claim that the other one is really involved with some very special operator, like just claim that, yeah. But here, U1 case, as this is the most interesting part, and you cannot separate them because U1 is actually diagonal. So that when you calculate the U1 SYK model or SUM global symmetry, then diagonal piece always get contribution both exponential and linear. But in this case, there is no M here because they are all related only diagonal, so that the effective M is 1. So always this one wins, so you don't have to worry about the large M. So conclusion is we saw the strong at the strong coupling limit we consider the some emergent symmetry and how we show that how it broken and leads to the effective action. And the singular fluctuation coupled to Schwarzian and the Lyapunov exponent is maximal. And on the other hand, the adjoint sector is get the contribution from the other effective action, which is trace JJ, and it grows linearly. So for this one, our recent ongoing work is it's natural to consider the 2D gravity and for example, Sachdev-Ye-Kitaev model or the general dilaton gravity and coupled to the gauge field, for example, U1 or any Yang-Mills, and it gives the same effective action, and you can work on then. You can, here the 4-point function, the contribution to the Lyapunov exponent from the effective action is you can repeat the same calculation in the bulk. So if you just obtain the effective action, the rest of them is just straightforward, just using this one, and you can just show that the effective action, the same calculation. And actually, this is also done. Schwarzian part is also discussed in the Maldassen and Stanford, and they very quickly show that. And the other is rank D tensor model. And so in rank D tensor model, I already mentioned that you can also separate calculate rigorously the 4-point function. There is various 4-point function, and some of them give the exponential, some of them grow linearly, and if you do the nice linear combination, and you can find some observer which grow only linearly or exponentially or nothing. And there is more interest storing here.
By D you mean Q, is it?
D is you say Q minus 1. And you can also do the supersymmetry generalization of this one, and this is also you can easily generalize supermetric formulation, and yeah, you can. This is also going on, and yeah, thank you very much. Yeah.
Any question from ICTS?
No questions.
All right. Any questions from Mumbai?
So you said that the symmetric part does not contribute. So what about the differ? So they only contribute to the decay modes.
Yeah. So yeah, so yeah,
Is
this
there a
is.
simple group theory argument to understand that they do not contribute?
First of all, effective action, from the effective action, it's very simple. So that this is nothing but gross theoretic argument, because epsilon does not touch any matrix structure. So does not touch it, so that this is just nothing but identity. So this part is easy, no contribution. This one is more like if you transform it, it becomes the anti-symmetric. So if you transform it, and you can easily expect that that would be related to some generator of the SOM, or and in this case, anti-symmetric. And actually, this is related to the eigenfunction of the other effective action, so that it's natural to think it as anti-symmetric. So that that's why there is overlap is 0. So that is one way to easily prove it. But the non-zero mode is slightly difficult. You have to work on the work with some 4-point function and the calculator. Yeah. So that is long calculation. And the one point is that yeah. So just the key point is that you can compare with this calculation, because it's very similar, but because there is no double pole. So here this is a simple pole, so that's why you don't have this kind of polynomial, and exponential is 0, so that you don't see nothing. Yeah, so that roughly speaking.
So you're saying that even if there is an exponential, it will be. You're not saying that there is an exponential, but it's further down orders in 1/p there. It's not like that. There is no exponential.
That part I'm not sure, because I only calculate here. What I calculate is the first of all quadratic contribution, which means that so up to this leading in the quadratic action. So there will be, if you consider the cubic and so on, maybe I don't know. And here also, I just consider the leading 1/beta j correction. It's not correction, so there will be, if you consider further correction, I don't know also.
Because the saddle bond itself will keep changing at every order of 1/beta. So then that.
Yeah, it is fine.
Okay, let's thank Junggi again.
Thank you.